I want you to imagine, just for a second, that you are tasked with building the ultimate artificial intelligence. And, I mean, we aren't talking about writing the software, or training the models, or coding the algorithms.
Right. You're not sitting at a keyboard writing Python.
Exactly. I mean,
Yeah.
you have literally been handed a blank check and told to construct the physical brain required to actually run the most complex neural networks in existence. You have to physically wire together the silicon, the memory, the storage, and the network. But, and here is the massive, unavoidable catch, when you have a machine that is processing, trillions upon trillions of calculations every single second, how do you keep that physical brain from literally melting down into a puddle of extremely expensive slag?
It's a great question because it really is the ultimate engineering bottleneck of our era. We interact with AI on our phones and laptops every day, so we tend to think of it as this weightless, ethereal thing that just, lives up in the cloud.
Yeah, it just feels like magic.
Right, but the physical reality of the cloud is incredibly dense. It is incredibly power hungry, and above all, it is incredibly hot. Like, the limits of artificial intelligence right now are actually just the limits of thermodynamics.
And that physical reality is exactly our mission for this deep dive, because we have a detailed architectural roadmap of how modern, massive-scale data centers are put together. Specifically, I'm looking at this August 2026 brochure for Supermicro's data center building block solutions.
Or DCBBS, as they abbreviate it.
Right, DCBBS.
Yeah.
And our goal today is to decode the physical foundation of the AI boom for you. We are going to look past all the slick tech buzzwords to understand the raw mechanics of how you power, connect, and crucially, cool the most powerful compute clusters on Earth.
Yeah, we have to look at this not just as a computer science document, but honestly, it's a masterclass in fluid dynamics and structural engineering. And logistics, too. It really forces us to synthesize raw hardware specs into a clear picture of how AI is actually constructed in the physical world.
So if you've ever wondered what happens out there in the real world, the moment you hit enter on a complex AI prompt, you're about to find out. But before we get into the flashing lights of the individual servers, we have to grasp the fundamental design philosophy driving modern data centers, which Supermicro lays out right away with this DCBBS concept.
Yeah, they describe it as a one-stop shop total solution.
Right, meaning they're integrating the computing, the power, the cooling infrastructure, the software, and the services all under one umbrella. And their stated goals for doing this are to speed up time to market and time to online, while reducing OpEx and CapEx.
Which are huge factors.
Let's start with those last two, actually. OpEx and CapEx. I mean, these are business terms, but they heavily dictate the engineering, don't they?
Oh, they completely drive the engineering. So CapEx is your capital expenditure. That's the massive upfront cost of, buying the servers, the racks, the cooling towers.
Writing the big checks.
Right, exactly. But OpEx is your operating expenditure. That is the ongoing, agonizing monthly cost of the electricity to run them and the water to cool them. When you are building infrastructure at this massive scale, a 1% inefficiency in OpEx can mean millions of dollars literally burned every single year.
Yeah.
So the engineering goal is always to drive both of those numbers down through hyper-efficiency.
Okay, that makes sense.
Yeah.
But I want to push back on the other two metrics they mentioned. Time to market versus time to online.
Okay.
Time to market is obvious. That's just how fast you can buy the hardware. But why is time to online treated as this separate, massive hurdle? I mean, doesn't buying the hardware essentially mean you are online?
Not even close. I mean, especially not at this scale. Time to market is just procurement. It means you've sourced your GPUs, your CPUs, and your racks, and the delivery trucks have actually pulled up to your loading dock.
Right.
But time to online is the grueling, deeply complex reality of getting tens of thousands of individual components to talk to each other harmoniously without catching fire or just constantly crashing.
Which I imagine is a nightmare.
It is. Historically, a data center operator would buy servers from vendor A, networking switches from vendor B, and cooling manifolds from vendor C. And then the IT team had to integrate all of that on-site.
And I'm guessing that integration isn't exactly plug and play.
Far from it. You run into firmware mismatches where a networking card just absolutely refuses to talk to a switch. Or you find out the cooling loops you bought don't quite fit the proprietary fittings on your server chassis.
Oh man, like buying the wrong size pipe at the hardware store.
Exactly. And then you spend months writing custom scripts just to get the telemetry data to show up on one single screen. The integration phase alone could take 6 to 12 months. So Supermicro's total solution approach is designed to provide the entire stack pre-integrated. They are trying to drastically shrink that time to online because in the AI arms race, if your hardware takes an extra 6 months to boot up,
You're already behind.
your AI model is obsolete before it even finishes its first training run.
Wow. Okay, so the strategy they use to build these massive environments is really interesting too. They talk about building complex systems like they use a 256 system node cluster as an example by dividing the build into smaller, highly manageable, scalable units.
Yes.
It's like playing with extreme high-stakes Legos. Instead of looking at an empty room and trying to wire 256 computers together piece by piece, you deploy them in these predefined blocks. So you aren't building a skyscraper brick by brick. You're snapping together fully furnished, pre-plumbed, pre-wired floors.
That's a perfect analogy. When you are dealing with a 256 node cluster, the complexity of the system isn't just additive, it is exponential. In a highly parallelized AI training run, if one single node fails, or one single cable causes a microsecond bottleneck,
Does the whole thing go down?
the entire 256 node cluster stalls. The whole supercomputer basically sits there twiddling its thumbs waiting for that one lagging node to catch
That's
up.
terrifying.
It is. So by creating a standardized, pre-tested, scalable unit, you mathematically mitigate that risk. You know that specific block of servers and switches works perfectly together. If you need more compute power, you don't completely redesign your network topology. You just stamp out another identical scalable unit and connect it to the spine.
Okay, speaking of network topology, they note that these scalable units are interconnected with a rail-optimized network topology. That sounds incredibly intense. Why does rail-optimized topology actually matter? Like when you, the listener, type a prompt into an AI, how does this specific networking setup get you your answer faster?
To understand rail-optimized topology, you really have to understand how AI learns. Large language models are so massive they cannot fit onto a single computer chip. They have to be sliced up and distributed across hundreds or thousands of GPUs. During a training run, these GPUs are constantly doing partial math problems and sharing the results with each other. If GPU number 1 has to wait for data from GPU number 2, it sits idle. So a rail-optimized topology is like building a dedicated multi-lane highway system between specific GPUs without any intersections, stop signs, or shared lanes.
So the data literally never gets stuck in traffic.
Exactly. In a traditional network, data packets bounce through various switches, sharing bandwidth with other traffic, which introduces latency-tiny delays. In a rail-optimized network, a GPU in rack A has a direct, dedicated rail to a specific GPU in rack B. The data flows with absolute minimal latency and maximum bandwidth.
Oh, I see.
So when you are at home waiting for an AI to generate a coherent paragraph, the speed of that response is entirely dependent on how efficiently those GPUs can talk to each other over those rails to process your request.
That is fascinating. So we have these pre-integrated blocks wired together with dedicated network highways. Now we need to look at what is actually inside the blocks, the compute and storage engines.
The heat generators.
Exactly, the massive heat generators of the whole operation. The brochure covers a really broad range of density, starting at 1U and going all the way up to 10U form factors.
We should probably define that measurement just because it's the fundamental geometry of a data center.
Yeah, we do.
So a U stands for rack unit.
Mm-hmm.
It is a standard measure of vertical height in server racks, and 1U is exactly 1.75 inches. So a 1U server is a very thin pizza box-sized machine.
Okay.
A 10U server, on the other hand, is 17.5 inches tall.
And this is where my intuition starts to clash with the brochure. Because for decades, the trend in technology has been miniaturization. We expect our phones and laptops to get smaller and thinner, but Supermicro is showcasing these absolute behemoths.
They really are.
Like they have a 4U NVIDIA HGX B300 system. They have an 8U HGX B300, which holds 8 GPUs. And they have an enormous 10U HGX B200, plus the Supermicro NVIDIA GB300 NVL72 system. And on the AMD side, they are supporting the multi-node 4U AMD MI355X. And they offer Intel Xeon CPU support alongside the AMD EPYC chips. But a 10U server is practically the size of a mini fridge, and it's filled entirely with processing power.
Right.
If the transistors on these chips are shrinking down to the atomic level, why are the server boxes themselves getting so massive? Aren't we moving backward in miniaturization?
It definitely seems contradictory at first glance, but it comes down to the sheer volume of processing required for AI and the physical support system that processing demands. You are correct that the transistors inside the NVIDIA or AMD chips are microscopic, but an 8U or 10U chassis isn't just holding the silicon chips.
What else is in there?
Well, it has to house the incredibly thick copper pathways required to move data between those 8 GPUs instantly, and more importantly, it has to house the colossal power delivery systems.
Right, the electricity has to get to the chip before it can do the math.
Precisely. You are pulling kilowatts of electricity into a single box. That requires massive voltage regulator modules, or VRMs, to step that power down and feed it smoothly to the processors. And finally, that 10U space is required to house the massive cooling infrastructure, which we will get to, just to keep those highly concentrated chips from instantly self-destructing.
So it's not that the chips are bigger, it's the life support system for the chip.
Exactly. We aren't moving backward in miniaturization. We are just packing an unprecedented, previously unimaginable density of compute into a single chassis.
And that density isn't just limited to the compute side either. The storage density is equally wild. The brochure details petascale all-flash systems designed specifically for high-performance AI.
Petascale is 1,000 terabytes, just for context.
Which is insane. They have object storage systems that can be front or top-loaded, and a massive 4U90 bay scale-out storage system. They support a variety of drive form factors, 2.5-inch, 3.5-inch E1s and E3s, including the E3's all-flash AI storage.
Lots of options.
But the key here is the interfaces they support: NVMe, SAS, and SATA. Now, I know SAS and SATA are older legacy connections, but why do you need petascale of NVMe all-flash storage sitting right next to the compute?
This solves what hardware engineers call the starvation problem.
Starvation.
Yeah. The NVIDIA B300 and AMD MI355X GPUs we just talked about are incredibly fast. They can process data at a blistering pace. But if you feed them data from traditional spinning hard drives or over an older SATA connection, the pipeline is simply too narrow. It's like trying to fill a swimming pool through a drinking straw.
Oh, wow.
Yeah, so these multi-million-dollar GPU clusters will spend 90% of their time just waiting for the data to arrive from the storage drives.
So they're literally starving for data to process.
Exactly. And this is where NVMe comes in. NVMe stands for Non-Volatile Memory Express. Unlike older SATA drives that had to route data through a controller hub, which created a massive bottleneck, NVMe drives connect directly to the PCIe bus of the motherboard.
So it skips the middleman.
Yes. It connects the storage almost directly to the CPU and GPU. It widens that drinking straw into a massive aqueduct. All-flash NVMe storage provides data at millions of input-output operations per second, ensuring those GPUs are utilized to their maximum potential. The storage architecture has to be just as extreme as the compute architecture, or whole system slows to the speed of the weakest link.
Supermicro also mentions their SuperBlade systems for AI and HPC high-performance computing, which offer the highest node density. But across all of these platforms, whether you are running NVIDIA, AMD, or Intel, they clearly state they offer a choice between traditional air cooling and liquid cooling.
And that is the huge pivot in the industry right now.
Right, because once you cram a mini fridge full of GPUs and NVMe drives into a rack, generating kilowatts of heat, air cooling starts to lose the battle with physics, doesn't it?
Air cooling physically cannot keep up anymore. Air is actually a terrible conductor of heat. Its specific heat capacity is very low. When you have a 10U server pulling that much power, you simply cannot push enough air through the chassis fast enough to carry the heat away.
Even with massive fans.
Even then, the fans have to spin at tens of thousands of RPMs, at which point they sound like jet engines, the vibration damages the components, and the fans themselves start consuming massive amounts of electricity just to spin. We have to change the medium of heat transfer entirely.
Which brings us to the intricate plumbing, because air is out and liquid is in. Supermicro is utilizing direct-to-chip liquid cooling, or DLC. They are placing specialized cold plates directly onto the hottest components to capture the heat with extremely low thermal resistance. But what struck me here is how comprehensive this is. They aren't just putting a cold plate on the main processor.
No, they have to cool everything.
Yeah, the brochure lists cold plates for the CPU, the GPU, the DEM, which is the memory, the VRM, the PCI switch, and even the PSU, the power supply unit itself.
The level of engineering here is truly microscopic, and it fundamentally changes the architecture of the motherboard.
I look at this like a human circulatory system. We aren't just putting a single ice pack on the forehead, meaning the CPU, and hoping the rest of the body cools down. We are running tiny, highly pressurized coolant veins to the memory modules, the network switches, and even the power supplies. But why do we have to cool a PCIe switch? I mean, it's just directing traffic. It's not rendering complex AI graphics.
Because of thermal throttling, which is the silent killer of AI performance.
How does that work?
In a traditional computer, if a component gets too hot, its safety mechanism is to slow itself down to generate less heat. That's thermal throttling.
Yeah.
Now imagine your massive GPU is perfectly liquid-cooled and running at 100%, but the VRM, that voltage regulator stepping down the power to feed the GPU, is only air-cooled. The VRM overheats, and to protect itself, it drops the power output. Your perfectly cooled GPU instantly loses power and slows down, or, as you mentioned, the PCIe switch. If the switch directing the high-speed data between the GPUs overheats and throttles, your data transfer speed drops. Remember the rail-optimized network we discussed earlier?
The dedicated highway, yeah.
It's totally useless if the on-ramp is overheated. Cooling every single critical component in the chain is the only mathematical way to sustain peak performance across a 256-node cluster.
Wow. So you really can't miss a single spot. And to manage this massive circulatory system, they use an in-rack CDU, or coolant distribution unit. This is a single unit that sits inside the server rack, and it has up to 250 kilowatts of cooling capacity.
That is a staggering amount of heat.
To put that in perspective, a standard space heater you'd plug into your wall at home is about 1.5 kilowatts. So this single box is handling the heat equivalent of roughly 160 space heaters running at full blast. It features a touchscreen, a web interface, and redundant pumps to secure power continuity.
Yes, redundancy is everything here.
Right, but they list two different redundancy standards here: EIA with 2N redundancy and OCP with N+1 redundancy. I need you to unpack this because this sounds like the kind of deep architectural decision that saves or costs millions of dollars.
It absolutely is, and it reflects the two different philosophies of data center design today. Let's start with EIA. This refers to the standard 19-inch equipment racks that have been the backbone of IT for decades. 2N redundancy in an EIA rack means you literally have two of everything.
Two of everything.
Yeah, two power feeds, two independent cooling loops, two separate CDUs. If System A completely explodes, System B takes over without a blip. It is bulletproof, but it is incredibly expensive because you are buying twice the hardware and only using half of it on a normal day.
Right, you're paying for a second car that just sits in the driveway just in case the first one breaks down.
Perfect analogy.
Okay, so what is OCP and N+1?
OCP stands for the Open Compute Project. This was an initiative originally spearheaded by hyperscalers like Facebook. When they started building data centers the size of shopping malls, they realized standard EIA racks were full of vanity features and wasted space. They redesigned the entire architecture to strip out anything that wasn't strictly necessary for computing.
Make it as lean as possible.
Right. And in the OCP model, they often use N+1 redundancy. N is the exact number of pumps or power supplies you need to safely run the system. The +1 means you add exactly one extra as a backup.
So instead of double the equipment, you just have a spare tire.
Correct. Through massive amounts of data collection, they calculated the exact mathematical failure rates of these pumps. They realized that the statistical likelihood of two pumps failing simultaneously is so microscopically low that buying a full 2N backup system is just a waste of capital. N+1 provides near-perfect safety while saving millions in CapEx.
That makes total sense.
Yeah.
Now, connecting the CDU to the servers is the CDM, the cooling distribution manifold. This is the main artery that distributes the cold liquid to each server and returns the hot liquid back. They offer horizontal mounting, but they specifically highlight a DLC2 vertical CDM. They note that mounting it vertically saves rack space and increases density.
Because in the data center, vertical rack space, those U slots we talked about earlier, is premium real estate.
Right, the 1.75 inches.
Exactly. If your manifold sits horizontally, it takes up 1U or 2U of space where a server could go. By engineering the manifold to run vertically down the very back corner of the rack alongside the servers, you reclaim that slot. It sounds minor, but if you gain one extra server per rack and you have 1,000 racks in your facility, you have just significantly increased your total compute power without having to pour a wider concrete foundation for the entire building.
It's all about hyper-efficiency. But this all brings up a massive physical anxiety for me. We are connecting all these cold plates and manifolds with host kits, and the brochure specifies they have a 10-bar liquid pressure tolerance.
Yes, 10-bar.
Which is roughly 145 pounds per square inch of pressure. My first instinct is absolute panic. We are pumping liquid at 145 psi right next to naked motherboards, processors, and memory. A microscopic leak at that pressure would spray coolant across millions of dollars of sensitive electronics in a fraction of a second. How is this risk mathematically justifiable, and how do they actually prevent catastrophic leaks?
It's justifiable because the alternative air cooling is no longer physically possible for AI workloads. But you are right to point out the risks, and the engineering reflects an absolute justified paranoia. A 10-bar tolerance is immensely over-engineered for the actual operating pressure, providing a massive safety margin. But the hoses aren't usually the weak point. The connectors are.
Right, where the hose actually meets the cold plate.
Exactly. Supermicro highlights their use of specialized ball valves that provide excellent sealing, preventing even the microevaporation of the coolant. They use universal cam locks for seamless locking integration to standard 1.25-inch CDU connections. The goal is a perfectly sealed, completely closed loop. Furthermore, the fluid itself is highly engineered. They specify an optimized PG25A coolant, which you can get in 20-liter, 200-liter, or even in 1,000-liter quantities. You can't just put tap water in these loops.
Why not? Water transfers heat really well.
Because of galvanic corrosion.
What's that?
If you run standard water through mixed metals like copper cold plates, aluminum radiators, and steel fittings, the water acts as an electrolyte. The metals basically start a slow electrical reaction that eats away at the material, eventually causing microscopic pinhole leaks. The PG25A coolant is chemically engineered for broad material compatibility across all the metals, plastics, and elastomers in the loop. It is designed to prevent corrosion entirely, ensuring long-term stability so the plumbing doesn't degrade over years of continuous use.
Okay, so we've successfully captured the heat from the microscopic silicon, moved it to the manifold, and pumped it to the in-rack CDU. But thermodynamics dictates that the heat doesn't just vanish, it simply moved. Now we have to figure out where it goes next.
Right, we have to get it out of the rack.
Exactly. This leads us to macro cooling. We have to zoom out from the individual rack to the row of racks and eventually the outside of the building itself. Let's start with the physical limits of the rack. The power shelf houses 6 5,500-watt high-efficiency PSUs with PMC and PoE with Redfish support. And the rack itself has a static load capacity of up to 2,500 kilograms. 2,500 kilograms. That is the equivalent of parking a mid-sized SUV inside a single server cabinet.
It's incredibly heavy.
You cannot just put that on a normal office floor.
Absolutely not. And this dictates the structural engineering of the building long before the IT equipment arrives. The sheer density of liquid-cooled servers, because, fluid is heavy, the dense copper cold plates are heavy, and the structural steel to hold it all is heavy. It requires reinforced concrete slabs. Standard raised flooring in older data centers will literally collapse under the weight of a DCBBS liquid-cooled rack.
That is wild. To handle a massive heat leaving that heavy rack, they offer a rear door heat exchanger, or RDHX. This is a brilliant piece of engineering. It literally replaces the back door of the server rack with a massive radiator. It has a cooling capacity of either 10 kilowatts or up to 120 kilowatts, pulling air through with N+1 high-performance fans. But the detail here that really requires explanation is the intelligent anti-condensation system.
That is arguably the most vital safety feature on the RDHX.
Really? Why?
Well, when you pipe cold liquid into a heavily air-conditioned data center, you are playing a very dangerous game with dew points.
The dew point.
Yeah. Dew point is the temperature at which air can no longer hold all its water vapor, and some of it condenses into liquid water. If the temperature of the coolant coils in the back of the rack drops below the ambient dew point of the room, condensation will form instantly.
Just like a cold glass of water sweating on a hot summer day.
Precisely. Now imagine a cold glass of water sweating, but that water is dripping directly down the back of a rack filled with live, high-voltage servers. Moisture in a data center is a literal death sentence for the equipment. It causes instant short circuits.
Oh, that sounds disastrous.
It is. So the intelligent anti-condensation system uses a matrix of sensors to constantly monitor the ambient temperature and humidity of the room. It mathematically calculates the dew point in real time and dynamically adjusts the temperature and flow of the coolant to ensure the coils always stay just above that dew point. It maximizes the cooling efficiency without ever crossing the threshold into sweating.
If the rear door heat exchanger isn't enough, we move out into the aisles with their in-row solutions. They offer a liquid-to-air sidecar CDU that supports up to 200 kilowatts. And then they have the absolute behemoth of the brochure, the in-row CDU with a cooling capacity of up to 1.8 megawatts. Both of these feature those N+1 pumps and redundant PSUs we talked about to prevent cooling interruptions, plus something called an ATS, an automatic transfer switch.
The scale we are talking about here is shifting dramatically. 1.8 megawatts of cooling capacity is enough power to run a small municipal neighborhood, and they are using that capacity purely to cool a single row of computers. At 1.8 megawatts of heat rejection, the automatic transfer switch is non-negotiable.
How does the ATS work in this context?
An ATS physically monitors the electrical feed coming from the utility grid. If the data center experiences even a microsecond power flicker or a full blackout, the ATS detects it instantly and mechanically switches the power feed over to the backup generators or battery arrays.
So it never loses power.
Right. In an AI cluster running at full bore, if the cooling pump stops circulating that fluid for even 10 seconds, the heat spike within the silicon would be catastrophic. The chips would either permanently damage themselves or trigger a hard, uncontrolled shutdown. The ATS ensures absolute continuous operation of the coolant flow, regardless of what the local power grid is doing.
We zoom out one more time, leaving the rows of servers and looking at the site infrastructure. This includes site-level cabling with optimized traffic engineering to reduce that time to online and save material costs. But the final boss of this entire thermodynamic journey is the water cooling tower. These towers support cooling capacities from 1 megawatt all the way up to 50 megawatts or more.
50 megawatts is huge.
It's massive. They use an EC fan design for energy efficiency, N+1 submersible pumps, and a closed-loop design to minimize maintenance. I really have to ask you to visualize a 50-megawatt water cooling tower for a second. We started this conversation looking at tiny copper cold plates the size of a playing card sitting on a GPU. Now we are looking at infrastructure that sounds and looks like a heavy municipal power plant. At what point does data center stop being a computer lab and just become a massive fluid management facility?
That is the open secret of the current AI revolution. Data centers are no longer just IT facilities, they are heavy industrial sites. The engineering of the cooling tower is just as important as the silicon. You mentioned the closed-loop design, which is vital for both maintenance and environmental impact.
What's the alternative to a closed loop?
Well, older data centers often used open evaporative cooling towers. They consumed millions of gallons of fresh water, passing air over the hot water and basically evaporating it into the sky to reject the heat. It was effective, but incredibly wasteful.
The cloud is actually very thirsty.
Extremely thirsty. But a closed-loop design keeps the primary coolant completely contained within a sealed system. The heat is transferred to an external loop without losing the internal fluid to evaporation. This minimizes continuous water consumption, which is critical because these massive facilities are increasingly scrutinized for their drain on local municipal water tables.
So we have 2,500 kilogram racks, 50 megawatt cooling towers, 145 PSI pressure hoses, and petabytes of flash storage. Human operators clearly cannot manage this manually. You can't just walk around a 1.5 million square foot facility with a clipboard checking analog pressure dials and thermometer readings.
No, human reaction time is orders of magnitude too slow for that, and the variables are far too vast. If a pump fails, you need a response in milliseconds, not minutes. You need a unified digital nervous system to control all this physical hardware.
Which brings us perfectly to the SuperCloud software suite. This is the brain managing the brain. First, they detail the SuperCloud Automation Center. This is pre-built, enterprise-grade automation that handles everything from firmware updates to OS provisioning to Kubernetes and AI workload enablement. What exactly are they automating here with Kubernetes?
Right, so Kubernetes is a container orchestration system. Think of it this way. AI workloads are highly complex applications. You don't just install them like a normal program, you package them in digital containers with all their required libraries and code. Kubernetes is the software that automatically decides which servers have the free capacity to run those containers, deploys them, and shuts them down when finished. The SuperCloud Automation Center manages this at the bare metal level.
Bare metal meaning exactly what it sounds like. No extra software in the way.
Exactly. In traditional cloud computing, you have a hypervisor, a layer of software that splits a physical server into several virtual machines. But hypervisors consume a small percentage of the CPU and memory. In high-performance AI, you want 100% of the hardware dedicated to the math. Bare metal provisioning means SuperCloud installs the AI workloads directly onto the hardware, bypassing the virtual layer entirely for maximum possible performance.
Then you have SuperCloud Composer, which provides unified rack scale and liquid cooling management. It monitors power usage and handles advanced leak detection, protection, and alerts. We talked about the physical hoses earlier, but how does the software actually handle leak detection?
That software leak detection is the ultimate safety net for the entire liquid cooling gamble. The software isn't just checking if a server is pinging on the network, it is constantly ingesting telemetry data from sensors inside the CDUs and manifolds. It monitors the flow rates, how fast the liquid is moving, and the pressure drops across the hoses.
Looking for anomalies.
Exactly. If Composer detects a sudden, tiny drop in pressure that doesn't align with the pump speed, the algorithm implies a leak has occurred. Before a single drop of water can even fall onto a motherboard, the software can automatically trigger a shutdown of the localized pumps and digitally isolate that specific rack.
That is incredible. The suite also includes SuperCloud Director, which acts as a multi-tenant AI cloud control. It integrates the bare metal provisioning, the storage management, and both Ethernet and InfiniBand networks. Let's pause on that network detail. We all know what Ethernet is. We use it every day. But what is InfiniBand, and why does an AI cluster need both?
Ethernet is incredibly versatile. It's the standard for general networking, getting data in and out of the data center to the wider internet. But Ethernet can suffer from slight overhead and latency issues when managing billions of tiny rapid-fire messages. InfiniBand is a highly specialized, ultra-high bandwidth networking protocol designed specifically for supercomputers.
How is it different in practice?
To use an analogy, Ethernet is the sprawling city street grid, great for getting anywhere but subject to traffic lights and congestion. InfiniBand is the dedicated high-speed rail line connecting two specific points. AI clusters use InfiniBand for the internal back-end network where the GPUs constantly talk to each other during training, and use Ethernet for the front-end network to interact with the outside world. SuperCloud Director has to manage routing rules for both seamlessly.
You mentioned multi-tenant control, which Director also handles. I assume this means securely dividing the cluster up for different users.
Precisely. Very few organizations buy a 256-node AI supercomputer and run only one single task on it continuously. It's too expensive. They lease out portions of it. Department A might need 64 nodes for a computer vision project, while Department B needs 128 nodes for a language model.
Oh, I see.
Director acts as the secure zoning board. It logically carves up the physical hardware, ensuring that Tenant A cannot see, access, or interfere with Tenant B's data, even though they are physically sharing the exact same storage arrays and InfiniBand fabrics.
But I have to push back on the logistics of this software. The brochure explicitly notes that Composer integrates with servers, networks, PDUs, CDUs, and third-party systems. We are talking about physical hardware coming from fiercely competitive companies: NVIDIA GPUs, AMD processors, Intel CPUs, third-party networking gear, and municipal facility cooling towers. Can one single software suite really act as a universal remote control for a liquid-cooled supercomputer made of so many disparate proprietary parts?
This is the exact hurdle that makes time to online so difficult, and it's why industry standards exist. Supermicro relies heavily on protocols like Redfish. We mentioned Redfish earlier regarding the PowerShell.
Right, what is that?
Redfish is an open industry standard specification for hardware management. It forces different hardware vendors to format their telemetry data like fan speeds, temperatures, and power, draw into a universal standardized API language. SuperCloud doesn't need to speak native NVIDIA or native AMD. It speaks Redfish. It ingests the standardized data from the GPUs, the CPUs, and the cooling pumps, and synthesizes it all into a single, actionable dashboard. That interoperability is the only way a system of this scale can function without collapsing under its own complexity.
The final piece of the software puzzle is the SuperCloud Developer Console. This brings together the AI pipelines, self-service provisioning, built-in observability, and something they highlight called GPU as a service, or GPU AS.
GPU as a service is where all of this terrifying physical infrastructure finally meets the end user. It is the ultimate democratization of hardware. It means a data scientist sitting in a coffee shop working on a lightweight, low-power laptop can log into this console via a web browser.
And just rent the hardware.
Exactly. They can click a button and provision a slice of that massive 10U NVIDIA HGX B200 we talked about. They don't need to know how to configure an InfiniBand network. They don't need to monitor the 10-bar liquid pressure cooling the chips. And they certainly don't need to worry about the 50-megawatt water tower on the roof. They just see a clean, ready-to-use digital environment to train their AI model. The developer console abstracts the physical reality away completely.
It totally abstracts it. So the scalable hardware units are chosen, the intricate liquid plumbing is designed, the SuperCloud software is loaded and ready. How does this actually get built, validated, and turned on in the real world? This takes us to our final exploration: validation, deployment, and global scale. Supermicro emphasizes that they don't just ship boxes of parts. They actively plan the floor plans, the rack layouts, and the precise port mapping. And crucially, before a single truck leaves their facility, they perform rigorous testing. They do rack-level testing, which they call L11, and cluster-level testing, which they call L12 validation.
This circles all the way back to our very first topic, drastically reducing the time to online. Historically, a vendor ships you 100 boxes, your IT team unpacks them, racks them, cables them, and turns them on. Statistically, in a shipment of 10,000 parts, a certain percentage will be dead on arrival.
Yeah, that makes sense.
A RAM module will be faulty, a fiber optic cable will be crimped, or a motherboard will have a microfracture.
I look at L11 and L12 testing like building a deep-sea submarine. You do not wait until the submarine is at the bottom of the Mariana Trench to find out if a hatch leaks. In L11 validation, they assemble the full rack in the factory. They put the components in a metaphorical pressure chamber, they power it on, they pressure test the liquid coolant loops for leaks, and they run grueling burn-in tests on the silicon to force any weak components to fail in the factory.
That's a highly accurate analogy, and L12 goes even further. L12 is testing the whole fleet of submarines together. They take those validated racks, network them together into the final 256-node cluster configuration using the actual InfiniBand switches, and test the complex interoperability. They ensure the data flows perfectly across the rail-optimized topology.
So they test the whole system before it even leaves.
Then and only then do they carefully pack it onto trucks. Finding a faulty optical cable or a tiny coolant drip at L12 in the factory takes 10 minutes to fix. Finding that exact same flaw when the rack is integrated into a live data center in the field requires shutting down the cluster, draining loops, and suffering millions of dollars in downtime.
When the validated systems do ship, they offer white glove delivery, which means on-site racking, stacking, and optional software installation by their technicians. And to back it all up, their global services offer a 4-hour on-site response time. This operation requires a truly global footprint. The brochure highlights their worldwide headquarters in San Jose, California, which is an over 1.5 million square foot green computing park. They also have an EMEA headquarters in the Netherlands, an APAC headquarters in Taiwan, and further logistical hubs in Malaysia, China, Korea, Japan, and the UK.
That massive geographic distribution isn't just a sales flex, it's a requirement for supply chain resilience and strict service level agreements. When you guarantee a 4-hour on-site response time to fix a critical failure, you have to have parts locally.
You can't put a manifold on a standard flight.
Exactly. If a liquid cooling manifold bursts in a primary data center in Frankfurt, you physically cannot wait for a replacement part to be manufactured and shipped from California. Having regional hubs with stock ready to deploy ensures the absolute minimum disruption to these highly critical, incredibly expensive AI workloads.
The ultimate promise they stamp across this entire architecture is twofold. First, to market innovation, meaning their systems are faster, and reduced environmental impact with a lower TCO total cost of ownership, meaning they are greener.
But I have a fundamental question for you, looking at this whole picture. We started this deep dive talking about the hypothetical task of building an AI. Considering the 1.5 million square foot manufacturing facilities, the massive capital required for 1.8 megawatt CDUs, and the global supply chains needed to pull off just a single DCBBS deployment, is building an AI something that only a handful of massive tech giants will ever actually be able to afford? It is the defining tension of the modern tech era. The raw compute power required to train a foundational frontier AI model, the massive large language models that make headlines, is indeed consolidating into the hands of hyperscalers and a few massive tech conglomerates. They are the only entities with the billions of dollars required to afford the 50-megawatt cooling towers and the 256-node clusters.
So the little guy is just out of luck.
Not exactly. However, the exact technologies we've explored today are actively trying to lower that barrier to entry. The shift from air to liquid cooling, the pre-validated scalable units, and SuperCloud's GPU as a service, these all serve to drastically reduce the total cost of ownership and OpEx. By making the infrastructure more standard, greener, and vastly more energy efficient, they ensure that mid-sized enterprises, research universities, and specialized startups can still afford to lease compute power, even if they can't afford to build the massive data center themselves.
So to summarize the incredible physical journey we've just unpacked, we started at the microscopic level, looking at a single NVIDIA or AMD chip operating at mind-bending speeds, generating intense heat. We saw how that heat is instantly captured by highly localized, pressurized copper cold plates. We followed that liquid through vertical manifolds out into massive 1.8 megawatt in-row distribution units, and eventually pumped all the way out to 50 megawatt closed-loop towers, rejecting heat into the atmosphere. We decoded the supercloud digital nervous system that monitors the pressure drops and routes the InfiniBand data, and we saw how these pre-integrated systems are stress-tested in the factory to save millions in the field.
We've managed to completely deconstruct the digital illusion of the cloud. It isn't weightless. It is made of dense silicon, reinforced steel floors, megawatts of electricity, and a massive amount of highly engineered pressurized fluid.
So the next time you, the listener, open a chat window on your phone to ask a quick question or prompt an AI to generate a piece of code, remember what you are actually doing in the real world. You are actively engaging those redundant pumps. You're pushing that specialized PG25A coolant through 10-bar hoses, and you are spinning up the EC fans on a massive cooling tower somewhere out in the physical world. You are directly commanding the heaviest infrastructure of the future.
It perfectly connects our daily, seemingly invisible digital habits directly to heavy physical engineering.
Which leaves us with a final thought to mull over. As our software and our AI algorithms become infinitely more complex, virtually weightless, and seemingly boundless in the digital realm, our physical infrastructure is running in the exact opposite direction. It is becoming heavier, vastly hotter, wildly more power-hungry, and incredibly dependent on pressurized fluids. What happens to the pace of innovation when the ultimate limiting factor for human artificial intelligence isn't our software ingenuity or our coding skills, but simply our physical ability to plumb, power, and cool the Earth?